Hey everyone, all the software you use every single day is really built on just a few incredibly powerful ideas. Today, we're going to deconstruct one of the absolute biggest, object-oriented programming, or OOP, and we'll do it using one of the most popular programming languages on the planet, Java. So let's just start with a huge question. When you look at a massive video game or a complex website, or even just the apps on your phone, how do you even begin to build something like that? It feels almost impossibly complicated, doesn't it? Well, the answer is actually surprisingly simple.
You start with a blueprint. Simple as that. You wouldn't try to build a house without one, and building software is really no different. You need a detailed plan, a design that describes exactly what you want to build. And this one core idea, it's the key to absolutely everything we're about to talk about.
First up, blueprints and real objects. We've got to get our heads around the crucial difference between the plan and the thing itself. In the world of programming, these two ideas have very specific, very important names. So first we have the class. A class is the blueprint. It's the template, it's the set of instructions that defines what something is and what it can do. And notice that key phrase on the screen. It's a logical entity. A class is just the idea, it's the description. It's not a physical thing taking up space in your computer's memory. Not yet. And that brings us to the object. An object is what you get when you actually use the blueprint to build something. It's the real, tangible thing that exists and takes up space. So if a class is the blueprint for a car, an object is the actual car rolling off the assembly line. And here's exactly what that looks like in Java. On the left, that class car code, that's just the idea, the blueprint. But on the right, see that small but incredibly powerful word, new? That keyword is like the factory. It takes the blueprint and actually constructs a real car object right there in the computer's memory. So why bother with this separation? Why not just build the thing directly? Well, it's all about efficiency. With that one single car blueprint, we can create thousands, even millions of individual car objects. They all follow the same fundamental rules, but each one can be its own unique thing. This is how we build massive, complex systems that are still predictable and organized. Okay, so what information actually goes into one of these blueprints? Well, a class really defines an object by describing two key things, what it has and what it does. As you can see here, we have properties. In code, these are called fields or instance variables. This is basically what an object has, things like its color, its weight, its name, and then we have actions. In code, we call these methods. This is what an object can do. It can accelerate, it can break, it can turn. These two parts, what it has and what it does, they define the essence of any object you create. Now, this is where things get really clever. What if you need a blueprint that's just a slightly more specialized version of one you already have? Do you have to start completely from scratch? No way. This brings us to our next big idea, inheritance. Inheritance is basically a way to create a hierarchy of classes, letting you go from very general concepts to much more specific ones. A new class, the child, can automatically get all the properties and all the actions of its parent class. It's like building on the work you've already done. So, for example, you might start with a really general blueprint, like a vehicle. It probably has basic properties and actions that pretty much all vehicles share, right? Like having a speed or the ability to move forward. Then you can create a more specific blueprint. And look closely at that keyword extends. This one word tells Java that a car is a kind of vehicle. So it automatically inherits everything from vehicle, and then you can add new things that are unique to cars, like having four wheels. And you can just keep going. A race car can extend car. So now the race car inherits from both the car and the vehicle blueprints, and it can add its own super specialized features like a turbocharger. You're creating this beautiful chain of specialization. This simple sentence really captures the whole idea perfectly. A specific thing, a bicycle, can be treated as its more general type, a vehicle. It's this simple is-a relationship that just makes perfect logical sense. So why is this a huge deal? It's all about code reusability. It means you only have to define speed one time in the vehicle class. And from then on, every future vehicle you ever create, cars, trucks, motorcycles, you name it, gets that feature for free. You write way less code, which means fewer bugs and much faster development. It's a massive win. Now, that simple fact we just established, that a race car can be treated as a car and a car can be treated as a vehicle,
That idea unlocks one of OOP's absolute greatest superpowers, polymorphism. I know, it sounds like a really fancy word, but polymorphism just means many forms. In programming, it means we can treat a car object or a bicycle object simply as a vehicle. By focusing on what they have in common, our code becomes unbelievably flexible. Take a look at this, for example. Imagine you have a virtual garage that's designed to hold vehicle objects. Because of polymorphism, we can park a car, a race car, and a bicycle all right next to each other in the same list. The garage doesn't need to know the specifics, it just sees them all as vehicles. The payoff here is just immense. It's all about flexibility. We can write much simpler code that just operates on vehicles in general, without having to worry about the tiny details of each different type. This makes our programs far more adaptable and way easier to expand in the future. Okay, so we've got our blueprints, we've got our objects, we've got inheritance, and we've got polymorphism. Let's put it all together now and see how these concepts actually build the digital world that's all around us. The truth is, object-oriented programming is literally everywhere. In a graphical user interface, that button you click on, that's an object. In a game, your character, the enemies, the items, yep, they're all objects. Even the really abstract data structures that organize all the information behind the scenes, like lists and trees, they're all built from these little interacting objects. It is the dominant way we build complex software today. So you see, in the end, OOP is so much more than just a set of rules or a programming technique. It's a philosophy. It's a way of looking at a really complex problem, breaking it down into logical objects that have their own properties and actions, and then figuring out how they all interact. It's really a way of modeling the real world right inside a computer. And that's where we'll leave it. From a single, simple concept, the blueprint, we can build entire worlds. So the final question I want to leave you with is this. If you could take anything at all, real or imagined, and model it as an object with its own unique properties and actions, what would you build?